Hello everyone, I'm Sangim at Guided Wave Analysis LLC. Today I would like to talk about dispersion curve and guided waves in pipeline. In every inspection we use waves. The wave travels along the pipeline and reflected from defect. We detect the reflected wave for finding defect location and its size. For guided wave testing of pipeline, we need to know the following three things. What kind of ultrasonic wave propagate in the pipeline? Which wave mode is the best for guided wave testing? And what is the velocity of distance calibration in the guided wave testing? What are guided waves? Guided waves are ultrasonic waves that propagate along lengths of the pipelines that confine the outer and inner wall of pipelines. Because many inspectors are familiar to ordinary ultrasonic testing, I would like to introduce the dispersion curve of ultrasonic wave mode in bulk steel first. This slide explains the longitudinal and the shear wave mode in the bulk steels. The main difference of two wave modes is particle displacement relative to wave propagation direction. The longitudinal mode has a particle displacement parallel to the wave propagation direction. Shear wave mode has a particle displacement perpendicular to wave propagation direction. This is a dispersion curve of bulk steels. Both the longitudinal and shear wave mode have a constant velocity because there is no geometric boundary along the wave propagation directions. The velocity is only dependent on the material properties such as modulus and density. The constant velocity of non-dispersive wave mode makes easy to the ultrasonic testing because the waveform does not change as the wave travels. In other words, it allows using one-cycle high-frequency tone pulse signal for high spatial resolution in finding defect at geometric features such as wells. This is a schematic drawing of pipeline for showing axial, radial, and circumferential particle displacement that are perpendicular to each other. The axial displacement is parallel to the wave propagation direction. That is a lengthwise direction of pipelines. In pipe cross-section view, the radial displacement along radius direction from the center of a pipe. The circumferential displacement is along the direction of angle change of a pipe wall. This slide shows the three wave mode in the pipelines, torsional, longitudinal, and flexural mode, depending on the particle displacement. The torsional mode is only circumferential particle displacement. The longitudinal mode has axial and radial particle displacements. The flexural mode has all three particle displacement of axial, radial, and circumferential directions. Three guided wave modes in pipelines are marked using the first letter T for torsional, L for longitudinal, F for flexural mode. The wave modes are written with two indexes of N and M. The first index of N is the number of symmetric axes in pipe cross-sectional view. The torsional and the longitudinal mode have 0 for first index. They are axial symmetric mode, and their particle displacement are the same at any angle of a pipe cross-section. But all flexural mode is non-axial symmetric mode starting from the number 1. The second index M is a numbering order starting from 0 kHz over frequency. This slide shows a comparison of a continuous MSS probe and discrete piezoelectric probe. It is very clear that the guided wave probe should be axial symmetry covering the whole pipe circumference for generating axial symmetry mode of torsional or longitudinal mode. If the probe is discrete along pipe circumference, it generates a flexural mode. That is a non-axial symmetry mode. The non-axial symmetry probe has a long dead zone and a near field length because it takes time to become axial symmetric waveform as a wave propagates. This is one example of a dispersion curve of 4.5 inch OD and 0.337 inch wall steel pipe. The plot shows a frequency for x-axis and group velocity for y-axis. There are so many modes. The question is which wave mode is best for guide wave testing. For answering this question, we must remember that what is the purpose of guide wave testing? It is finding defects. For finding defects, we need to transmit an ultrasonic wave having high spatial resolution with one cycle in the low-frequency ultrasonic wave testing. I'll explain it more in the following 2 slides. This shows a transmitted signal over 1 to 6 cycle and its frequency spectrum. The 1 cycle RF signal has a narrow time width so that it is a broadband with a wide frequency width. The 6 cycle RF signal has a wide time width and a narrow frequency band. In guide wave testings, we need to use 1 cycles for having high spatial resolutions because the narrow time width has a narrow signal width. This slide shows a signal waveform of a transducer in ordinary UT inspection. It is copied from the Understanding of Ultrasonic Transducer in Olympus brochure. Even though the ordinary UT is operating at high frequency, such as 5 MHz, only 2 cycles are used for having high spatial resolution even in narrowband transducers. If guide wave testing uses 6 or more cycles at 32 to 128 kHz operation, it is nonsense with a poor spatial resolution of signal width of 1 to 3 feet. The guide wave testing must use 1 cycle for improving the spatial resolution. Then we can find the defect at and near the pipe spot or other geometric features with a high spatial resolution signal over 1 cycle. This slide shows the RF and its spectrum plot over 1 cycle transmitted signal. The RF signal in time domain can be transformed into signal amplitude in the frequency domains by doing the fast Fourier transform. The RF signal can be represented by the weighted sum of the sinusoidal wave over frequency. Both are the same except they are plotted in different domains over time and frequency. Let us assume we are using 64 kHz center frequency probe for guide wave testing. For showing the difference of dispersive and non-dispersive wave mode, let us consider the T01 and F22. The T01 is a fundamental torsional mode and non-dispersive at any frequency, but F22 is a dispersive mode that has a varying group velocity as the frequency changes. The 1 cycle transmitted signal includes several frequency components of, for example, 45, 55, 64, 70, and 80 kHz. The non-dispersive T01 mode has a constant velocity at those frequencies, but the dispersive F22 mode has a different velocity depending on the frequencies. Let us consider the guide wave has reflected from an object at 15 meters. We can calculate the RF waveform by using inverse FFT process. This is the RF waveform, the comparison of T01 and F22 mode after the round trip distance of 30 meters. The transmitted signal is the same for both wave modes, but the received signal are located at different distance because of the group velocity differences. The T01 mode has the same waveform of that of transmitted signal, but dispersive F22 mode has an elongated waveform depending on the frequency. The wave packet of dispersive mode waves broadens as the wave propagates. This slide explains the purpose of guide wave testing. It is finding defect using signal-to-noise ratio and spatial resolutions. The non-dispersive wave mode has the highest signal-to-noise ratio and high spatial resolutions because the signal at different frequencies has the same velocity. On the other hand, the dispersive wave mode has a poor signal-to-noise ratio and a poor spatial resolution because the signal at different frequencies travels at different velocities. As the waves travel longer distance, the signal-to-noise ratio and the spatial resolution gets worse for dispersive wave mode. For long-range guide wave testing, we must use a non-dispersive wave mode. We are back to dispersion curve of pipeline. The only non-dispersive wave mode is T01, and all other wave modes are dispersive. For increasing spatial resolutions, the transmitted signal uses one-cycle tone-burst RF signal that is broadband with a wide frequency spectrum. All dispersive modes are curved lines so that the group velocity changes as the frequency changes. These dispersive modes cannot be used for long-range ultrasonic testing due to broadening of wave packet. If you look at the dispersion curve, you will find L02 mode that are almost a constant velocity in the wide frequency range. In these examples, we can see that the velocity of L02 mode is almost a constant between 40 and 100 kHz. But T01 mode is better than L02 mode because of the following merits. First, T01 mode is not affected by liquid content in pipelines. If the pipeline is carrying liquid, L02 mode will generate a trailing signal in every reflector in the pipeline because the longitudinal mode travels through the liquid in the pipelines with a slower speed than that of the steel pipe wall. Second, the T01 mode has the higher sensitivity than L02 mode at the same frequency inspection. Third, the T01 mode has no dispersion at any frequency and any size of pipelines. But L02 mode is dispersive. In this example, L02 mode is dispersive between 18 to 35 kHz. Fourth, T01 mode can find axially oriented defect if it is 70% or bigger wall loss. Now we found that non-dispersive T01 mode is best for guide wave testing. The best mode in the guide wave testing of a pipeline is a fundamental torsional mode T01 with the following merits. First, it has no dispersion at any frequency and any size of pipelines. Second, it has only circumferential particle displacement, so that it has minimal complication with other wave modes that has radial and axial particle displacement. Third, it is easy to generate with magnetostrictive guide wave testing equipment. After knowing the T01 mode is best, magnetostrictive and piezoelectric transducers were made for generating circumferential particle displacement, either coupled to outer surface using shear couplant, dry coupling, or epoxy bondings along the pipe circumference for generating T01 mode. Because the transducer is only coupled on the outer surface of a pipeline as a non-destructive testing, particle displacement in the middle and the pipe wall is decided on the nature phenomenon of shear particle propagation through the pipe wall. It is decided on the frequency of a tone burst transmitter. As the frequency increased, the probe generated other torsional wave modes, such as the T02 mode. The T01 mode is free from the dispersion-related problem to the cutoff frequency of T02 mode. The T02 mode is generated if half period of a tone burst transmitter is shorter than the travel time of T01 mode along the wall thickness. This slide shows the particle displacement in the pipe wall for T01 and the T02 mode. T02 mode is firstly generated when the wall thickness is equal to half wavelength. We call it as a cutoff frequency of T02 mode. If we operated the frequency less than cutoff frequency of T02 mode, the non-dispersive T01 mode is only generated in the pipe wall. This is dispersion curve of 8 MPS and Schedule 40 pipeline. Because we only generated the circumferential particle displacement with a guide wave probe, we only plotted the torsional mode by removing longitudinal and flexural modes. Three wave modes of T01, T02, and T03 are shown. The T02 and the T03 are dispersive. The cutoff frequency of T02 mode is 198 kHz with a 0.322 inch wall pipeline. At the cutoff frequency, the wavelength is equal to twice of wall thickness. What is the cutoff frequency of T02 mode? We'll see that the cutoff frequency of T02 mode is decided on the wall thickness of the pipelines. The torsional guide wave is a connection between ultrasonic wave and the geometric feature and the wall thickness of pipelines. The cutoff frequency tells us what frequency should we use for generating non-dispersive T01 mode in the field testings. Because the cutoff frequency is calculated with the wall thickness of a pipeline, we firstly ask the client the wall thickness of pipeline. If the wall thickness is 0.322 inch or thinner, we can operate 64, 90, and 128 kHz center frequency for inspection. The high-frequency guide waves allow us finding smaller volume defects such as accumulated peeling corrosion defect. This slide shows the generation of only T01 mode at 64 kHz center frequency. The 64 kHz is much lower than 198 kHz, the cutoff frequency of T02 mode. This slide shows the generation of T01 mode with a 128 kHz center frequency probe in 0.322 inch wall pipeline because 128 kHz frequency is much lower than the cutoff frequency of T02 mode. This slide shows the generation of both T01 and T02 mode with a 250 kHz center frequency probe. The 250 kHz center frequency is higher than the cutoff frequency of T02 mode. The generation of two modes makes it difficult to do data analysis because each reflector in pipeline has two signals of T01 and T02. In long-distance inspection, the dispersive T02 mode increases the background noise level of data with a very long duration of signal with different velocities. In this example, the velocity of T02 mode is between 0 and 100 inch per millisecond. This slide shows the dispersion curve of bulk steel and 4 MPS steel pipelines. The dispersion curve of bulk steel was drawn with dotted blue lines. The dispersion curve of 4 MPS steel pipe is plotted with solid black lines. Please check the difference between T01 mode in 4 MPS steel pipe and shear wave mode in bulk steels. They are the same in dispersion curves and particle displacement relative to the wave propagation direction. We can conclude that the T01 mode in guide wave testing in steel pipe is equivalent to shear wave testing in steel pipe. Now let's talk about distance calibration in the guide wave testing. The velocity of T01 mode is used for distance calibration of a report. All entity equipment only record time and electric voltage. In the reporting process, we need to calibrate the distance by inserting velocity of a transmitting wave. If client asks what kind of guide wave mode do you use in guide wave testing, the answer is T01 mode, not torsional mode. There are many torsional modes of different velocities. Some guide wave systems plot the data saying those data as torsional and flexural modes. They are wrong because there are so many torsional and flexural modes in pipelines. They should say exact mode so that they can calibrate the distance by inserting its velocity. Let me conclude my presentation. The guide waves in pipelines are plotted in dispersion curve. They are torsional, longitudinal, and flexural mode depending on the particle displacement. The best wave mode in guide wave testing of pipeline is a T01 mode that has a constant velocity at any frequency and any size of pipeline. The long-range guide wave testing uses a non-dispersive T01 mode at the frequency lower than cutoff frequency of T02 mode. The guide wave testing in pipeline is simply low-frequency shear wave testing with the operation of T01 mode. The velocity of selected wave mode is used for calibrating distance with its velocity in the guide wave testing report. Thank you for your attention. If you have any questions, please email me at skim@gwanalysis.com. Bye.